Today we're going to talk about buffer solutions. So buffer solutions are solutions that resist change in pH with small additions of acid and bases, and this is how our body stays in equilibrium. Most of the things in our body works off of buffers, so our pH stays relatively constant within our different areas and solutions in our body. So a weak buffer solution is always a combination of a weak species and its conjugate. So here I have a weak acid and a conjugate base, but it can also be a weak base and a conjugate acid. So a lot of times when they make buffer solutions, they take a weak acid and they put in a common ion, which is the salt of a weak acid. That way I have my weak acid, I put it in, and I have my conjugate base from the salt. And then I can make certain buffer solutions based on the pH that I want. And we'll talk about that in another lesson. So what we need to do is we need to understand this titration curve. So we have a weak acid. Here's my telltale little swish at the beginning. And then this area right here is my buffer. And why is that? Well, I start with that weak acid, and I am going to add my base. As I add my base, I start eating up those hydrogens and I produce this conjugate base. So as soon as I start titrating, I have my acid and my conjugate base in solution. Now, once I hit neutralization, okay, all of the OHs has eaten up all of the H pluses from HCN, so this is gone now, and now I only have OHs and Cl. So I don't have a buffer anymore. Okay, so you only have a buffer at the beginning of those titrations, and notice Na is a spectator ion, so what we're really looking at is that Cl minus, which is going to start being produced right away, and it's going to stay there the whole time. But my pH starts going up because my weak acid starts going away. Okay, so that is your buffer titration curve, and you always get a buffer region when you have a weak species. Okay, so how do these buffers work? They work based on Le Chatelier's principle. Okay, so here I have no buffer. I have a strong acid and a strong base, and so I don't have a weak species, which means I don't have an equilibrium to go with my conjugate base. So it doesn't go back and forth. That means that when I add additions of HCl or OH, it just keeps going to the right, and I can't adjust that pH. Okay, so let's look at this. This is my buffer, and this is my HX, and this is weak. Okay, when I have the weak acid in solution without titration at all, it makes this conjugate base and it's in equilibrium. So now if I rearrange this, I have my H plus. This is what drives my pH. And when I add my HX, it drives it over there, and I start making more. So these two go up, and this doesn't change very much. Conversely, if I add something that will react with one of these, like an acid or a base, it will drive the equilibrium to keep this relatively constant, to keep my pH constant. Okay, so if OH is added, okay, it's going to react with my HF, and it's going to shift right. So I wrote the reaction. So I had hydroxide, which should increase the pH, but it gets eaten up by this H plus, and it makes more of this. So it keeps it relatively constant. Conversely, if I add H plus, we're going to shift left, and we're going to have less X. Okay, it's going to react with X, and it keeps this relatively constant. So we have relatively small changes with a very small KEQ, which means we can keep this H plus relatively constant, and that's how they work. I have two videos for you to look at this to explain it more. So how do we make a good buffer? We make a good buffer usually with a weak acid and the salt of a weak acid. okay? Or we can take a weak base and the salt of the weak base. So number 2, we are going to look at this titration curve, and you're going to see that my pH equals my pKa for a perfect buffer. And so we can choose our buffer with a specific pH, okay, and that's chosen by the pKa of the weak acid. So we're going to look at this titration curve mathematically, and we're going to do that using the Henderson-Hasselbalch equation. And remember, back here, we rearrange this to look at our H plus concentration. So if I take the negative log of both sides and rearrange it, I have the star here because I have a video on how they go through and derive the Henderson-Hasselbalch equation. But when you do that, you're going to get this. That way, if I know my pH and I know my pKa, I can find these concentrations. So you can solve for a lot of things here. I can figure out this ratio if I have the pKa and solve for the correct pH of the buffer. Okay, but what's most important here to look at is that, remember, my perfect buffer contains equal concentrations of A- and HA+. So if these two are equal, I'm taking the log of 1, and the log of 1 is 0, so that drops out. So my perfect buffer is when my pKa equals my pH. So right here, what we have is a buffer where my pKa equals my pH. So if I didn't know my pKa, I can just find this buffer area, and right in the middle of it is when my concentrations are equal. It's called the half equivalent point, where HA equals A-. Okay, that's my half equivalence point, and I can go over and see this is a pH of 6, which means my pKa is also 6. And they call it the half equivalence point because it's halfway to equivalence point. So if I have 20 milliliters here, that'd be 10 milliliters. If I have 2 moles there, that would be 1 mole. Okay, because remember, our equivalence point is where moles of A equals moles of B stoichiometrically. So we can use this buffer graph to figure out our pKa if we need to. We can find the pH of that perfect buffer. If we know how much volume it took to get to our buffer, our perfect buffer, I would know how much volume to get to my equivalence point. Okay, so half equivalence point is half the amount of the titrant used. So half the moles to get to equivalence point. Okay? And so how do we make that perfect buffer solution? Well, we need that weak acid, and a salt of a weak acid is usually how they make it. I can titrate with an acid to get to this point, but they usually use this because then we can use our equation and we can know the concentration of our species to get our perfect pH. Okay? Buffers at a specific pH is chosen by the pKa of the weak acid.